So we have mathematical methods in physics practice final exam. So let's begin. This is part one. And number one, evaluate exactly I of A equals integral from negative infinity to infinity x squared over this quantity x squared plus 1 times this quantity x squared plus a squared dx, where a is greater than 0, a cannot equal 1. So for part A, construct an appropriate contour. For part B, identify all poles and classify singularities. Part C, compute residues explicitly. Part D, derive a closed form expression for I of A. And for part E, show the limiting behavior as A approaches 1. So for this one, we're going to use the standard upper half plane semicircular contour. We're going to let f of z equal z squared over z squared plus 1, z squared plus a squared. And that's going to equal z squared over z minus I, z plus I, z minus IA times z plus IA. So the appropriate contour for this, c sub r, is that interval from negative r to r. And that's union re I to theta, where 0 is less than or equal to theta is less than or equal to pi. And we're going to let r approach infinity here. Okay, so this is the real line plus a large semicircle in the upper half plane. And since f of z is asymptotic to 1 over z squared, that absolute value of z is going to approach infinity, and the semicircle contribution goes to 0. Okay. For part B here, the singularities are going to be at z equals I, z equals negative I, z equals IA, z equals negative IA. And since A is greater than 0, the upper half plane poles are z equals I, z equals IA. All are simple poles, provided A does not equal 1. If A equals 1, z equals I becomes a double pole, which is why the original problem assumes A cannot equal 1. Okay, for part C, the residues. So for this, sorry about that, part C, at z equals I, residue f at I here, that equals a limit as z approaches I, z minus I, z squared over z minus I, z plus I, z squared plus a squared. So that equals I squared over I plus I times I squared plus a squared. So that's equal to negative 1 over 2I times the quantity a squared minus 1. So the residue of f at I, that equals I over 2 times the quantity a squared minus 1 when we simplify. At z equals IA, residue f at IA equals a limit as z approaches IA. Z minus IA times this quantity z squared over z squared plus 1, z minus IA, z plus IA. That equals IA, that quantity squared, over parentheses IA quantity squared plus 1, close parentheses, and then parentheses IA plus IA, close parentheses there. And that equals negative A over quantity 1 minus A squared 2IA. So residue of f at IA is negative IA over 2 times quantity A squared minus 1 when we simplify that. And then if we take the sum of these residues here, residue f at I plus residue f at IA, that's I over 2 times quantity A squared minus 1 minus IA over 2 times quantity A squared minus 1, which is I times the quantity 1 minus A over 2 times the quantity A squared minus 1, which is negative I over 2 times the quantity A plus 1. Okay, and for the remainder of the problem here, let's see if we have the following integral here, negative infinity to infinity x squared over x squared plus 1, x squared plus a squared dx. Evaluating that, we're going to get 2 pi I times the quantity negative I over 2 times the quantity a plus 1. And I of A is going to equal pi over a plus 1. And as A for letter E approaches, as A approaches 1, I of A is going to approach pi over 2. Okay, so that's all for number 1. And now moving along to number 2. So number 2, we have the following. Sorry about the delay here. So number 2, we have consider the periodic function f of x equals x cubed. Interval negative pi is less than x is less than pi, extended periodically. Part A, derive the full Fourier series. Part B, determine whether the expansion contains sine terms, cosine terms, or both. Part C, prove convergence properties at x equals pi. Part D, using Parsifal's theorem, derive the exact identity for the sum n equals 1 to infinity 1 over n to the 6th without appealing to known zeta function identities. So Fourier analysis, f of x equals x cubed, interval negative pi is less than x is less than pi. Since x cubed is odd, the Fourier series contains only sine terms. So x cubed is asymptotic to this sum n equals 1 to infinity b sub n sine of nx. So our coefficients here are going to be b sub n equals 1 over pi times the integral from negative pi to pi, x cubed sine of nx dx. Now from here, that's 2 over pi. We could change it to 2 over pi times the integral from 0 to pi x cubed sine of nx dx. And then after integrating by parts, this integral from 0 to pi x cubed sine of nx dx, that becomes negative pi cubed times negative 1 to the n over n plus 6 pi times negative 1 to the n over n cubed. So, building on that, b sub n equals 2 times negative 1 to the n, parentheses, negative pi squared over n plus 6 over n cubed, close parentheses. And from there, so x cubed equals this sum, n equals 1 to infinity, 2 times negative 1 to the n, times negative pi squared over n plus 6 over n cubed sine of nx, for negative pi is less than n is less than pi. And at x equals pi, the periodic extension jumps from pi cubed to negative pi cubed, so the Fourier series converges to the midpoint 0. And continuing with number 2, using Parsifal, 1 over pi times this integral negative pi to pi x cubed, x to the 6th rather, dx, equals a sum n equals 1 to infinity b sub n squared. The left side, it's going to be 1 over pi times 2 times the integral from 0 to pi x to the 6th dx. That comes out to, when we perform the computation, 2 pi to the 6th over 7. The right side, b sub n squared, that equals 4 times the quantity x to pi to the 4th over n squared minus 12 pi squared over n to the 4th plus 36 over n to the 6th. So 2 pi to the 6th over 7 equals 4 pi to the 4th times this sum 1 over n squared minus 48 pi squared times the sum of 1 over n to the 4th plus 144 times the sum 1 over n to the 6th. So using that sum, 1 over n to the n squared equals pi squared over 6. Sum 1 over n to the 4th equals pi to the 4th over 90. We're going to wind up getting this sum from n equals 1 to infinity. 1 over n to the 6th equals pi to the 6th over 945. Okay, so that's the first part. Thank you very much and have a great day.